Next, we are going to discuss demodulation of PAM signal. For the detection of PAM signal, the frequency domain is the right platform. So, before discussing demodulation of PAM signal, we first convert PAM signal from time domain to frequency domain. So, in time domain, PAM signal is denoted by G function of t, and it is equals to convolution of m del t and ht. And we know that the Fourier transform of convolution of two signals is simply the multiplication of their individual Fourier transform. And here PAM signal, that is G function of t, is in time domain and its frequency version is denoted by capital G function of f. So G function of f is simply multiplication of Fourier transform of m del t and Fourier transform of ht, that is denoted by capital letters. Now, as we know that m del t is equals to summation n equals to minus infinity to infinity m nts into del t minus n ts, and in frequency domain it is capital M del function of f equals to fs summation k equals to minus infinity to infinity m f minus k fs. Here fs is sampling frequency and k is any constant that varies from minus infinity to infinity. So after substituting m del function of f, we get PAM signal in frequency domain, that is capital G function of f equals to fs summation m function of f minus k fs into h function of f. But there is a disadvantage of using pulse amplitude modulated signal to transmit information directly. During transmission of PAM signal, which carries some information, undergoes a distortion that is called aperture effect. This aperture effect is introduced because of considering standard rectangular pulse ht of unit amplitude and duration capital T. In frequency domain, standard rectangular pulse having sinc function, that is noted by capital H function of f equals to t sinc function of ft e to power minus j pi f into t. And the amplitude response of standard rectangular pulse is shown in figure, that having a sinc response. The amplitude response, that is mod of hf, is equals to t sinc function of ft, because we know that mod of e to power minus j pi ft is equals to 1. As the amplitude response mod of hf having variation in amplitude at each instant of frequency scale from minus infinity to infinity, there introduce an amplitude distortion with a delay of t by 2. Since frequency is inversely proportional to time period. And this distortion, that is based on the flat top sampling, is called a aperture effect. So while transmitting PAM signal, there includes an aperture effect which is undesirable, so it should be removed at the receiver side. Now, for the recovery of the modulating signal MT from PAM signal with an aperture effect, we first pass PAM signal in frequency domain, that is G function of f, through a low pass filter and then followed by an equalizer. The function of the equalizer is to reduce the aperture effect. So the demodulation of PAM signal is shown by block diagram. It consists of reconstruction filter, that is a low pass filter type, and equalizer. The function of equalizer is to suppress aperture effect. So the input PAM signal is in frequency domain. This input signal contains both low frequency as well as high frequency component. And after passing through reconstruction filter, that is low pass filter, and its frequency response is h function of f, and the resulting filter output is equals to mf into hf. Here it is assumed that modulating signal is band limited signal with a bandwidth of W, having sampling rate of fs greater than twice of W. So the high frequency components are assumed to be cancelled, and we have only low frequency component similar to message spectrum m function of f. And the output of low pass filter is the product of mf and frequency response hf. And it is equivalent to the situation when a message signal is again passed through the another low pass filter of transfer function hf. Since output of low pass filter is product of mf and hf, which means that the message signal amplitude is distorted because of the standard rectangular pulse hf. And this phenomena is called an aperture effect. In order to correct this distortion, we use equalizer after the low pass filter. The function of equalizer is to decrease the losses of reconstruction low pass filter within the bandwidth of W. Here the aperture effect is compensated by equalization, which is obtained by increasing the frequency of reconstruction filter. And the amplitude response of ideal equalizer is inverse of mod of hf, and it is equals to 1 upon t sinc function of ft, that is equals to pi f upon sine pi ft. In practice, for duty cycle t upon ts less than or equals to 0.1, the amplitude distortion is less than 0.5%. So the amount of equalization is usually very small, and there is no need of equalization in this situation. So here the equalizer has inverse amplitude response, and at the output of the equalizer we have modulating signal. Next we discuss transmission bandwidth of PAM signal. For this, let us consider a practical flat top sampled PAM signal with tau as width of each pulse and Ts as duration between adjacent samples. Here width tau is very small as compared to sampling period Ts, and according to sampling theorem, for proper recovery of modulating signal, the sampling frequency is always greater or equals to twice of W. Here W is the message bandwidth. So sampling frequency is equals to 1 upon Ts, that should be greater or equals to twice of W. Or we can say that sampling period is less than or equals to 1 upon 2W. Now using equation 1, that is tau less than or equals to Ts, in place of Ts we can write 1 upon 2W, and this results tau less than 1 upon 2W, or bandwidth W is less than 1 upon 2 tau. So in order to transmit and receive of PAM signal without any distortion, the transmission bandwidth must satisfy the equation. And according to this equation, the transmission bandwidth is greater or equals to 1 upon 2 tau. That should be greater than W, that is message bandwidth. Secondly, from the bandwidth conservation point of view, as transmission bandwidths decrease, the width of each pulse tau increases. But this will introduce an aperture effect which is undesirable, and this may be corrected using equalizer at the receiver side. Beside aperture effect, PAM signal is also affected by noise. During transmission of PAM signal over a communication channel, the noise gets added due to its additive nature. Figure shows the effect of noise on PAM signal. Here noise is superimposed on PAM signal and the flat top gets distorted. Since information is within amplitude of PAM signal and due to additive noise, the information gets contaminated. And this results very poor noise performance. So we go for other pulse modulation technique which has better performance, and these are PWM, that is pulse width modulation, and PPM, that is pulse position modulation.